Hi everyone, hope everybody is doing well, staying safe and healthy. Okay, all right, so this is the second session for our chapter 18. Let's see, so we talk about autoionization of water in the last slide, right? So we talk about that the two water molecules can take up one proton, hydrogen from one water molecule and become hydronium ion and hydroxide ion. We said that is called autoionization or self-ionization of water. Okay, so basically two water molecules can give you a hydronium ion and a hydroxide ion. Okay, now let's see what is ion product constant for water. It is given the symbol Kw. Okay, so we have seen this equation before. Two water molecules, liquid water, hydronium and hydroxide ion. Now if you write the Kc for this expression, your products are going to be hydronium ion and your other product is hydroxide, and you have two molecules of water, so water raised to the power 2. Normally the concentration of water is huge, right, and we can consider it as a constant. So if you take this water raised to the power 2 into the same side as Kc, now we have this term Kc times concentration of water raised to the power 2, and we can come up with a new constant to represent both of these called Kw, which is called the ion product constant for water. Meaning Kw now equals concentration of hydronium ion times the concentration of hydroxide ion. Now experimentally found out this ion product constant for water has a constant value which is 1 into 10 to the negative 14 at 25 degrees Celsius. Okay, so this is a known constant. Now in pure water means it has a same amount of hydronium ions as the same amount of hydroxide ions. Basically they both are the same, right? So this times this is 1 into 10 to the negative 14. Since both of them are equal amounts in pure water, if you take the square root of 1 into 10 to the negative 14 will give us the concentration of either the hydronium ions or the hydronium ions, which is 1 into 10 to the negative 7. So in pure water, if you take hydronium ions or hydroxide ions, concentration of that is going to be square root of Kw of water, which is 1 into 10 to the negative 7. So both ions are present in all aqueous systems. If you take any kind of aqueous system, you have hydroxide ions and hydronium ions. They are going to be equal in pure water. But in other aqueous systems, you can have maybe more of hydronium ions, maybe more of hydroxide ions, okay, depending on the pH of the solution. And the ion product constant for water, Kw, and acidic basic solutions. A change in hydronium ion concentration causes an inverse change in hydroxide ion concentration and vice versa. If you change the hydronium ion concentration, you change hydroxide. If you change hydroxide ion concentration, you change hydronium ions. So if you have higher hydronium ion concentration, meaning you have lower hydroxide. If you have higher hydroxide, you have lower hydronium ions. And then the product of this always going to be 1 into 10 to the negative 14. Okay. So we can define the terms acidic and basic in terms of relative concentrations of hydronium ions and hydroxide ions. In an acidic solution, we have more of hydronium ions. It's going to be more than the hydroxide ions. In a neutral solution like pure water, hydronium ion concentration and hydroxides are the same. And in a basic solution, hydroxide concentration is more compared to the hydronium ions. So H3O plus represent the acidity of the water. Acidic form of water is represented by hydronium molecule. Okay. The relationship between hydronium and hydroxide and the relative acidity of solutions. Now in pure water, hydronium ion and hydroxide are the same or neutral solution. Pure water or neutral solution, meaning pH 7. And that can be divided into Kw. Remember, the product of this is the Kw. And if you have more hydronium ions compared to hydroxide, meaning that is going to be acidic solution. Acidity is represented by the color red because the pH paper gives you a red color if it is acidic solution. Okay, that's why we have red and blue. So pH paper gives a blue color if it is a basic solution. So if you have more of hydroxide compared to hydronium ion, that is a basic solution. Okay. And in a neutral solution, if you put a pH paper, nothing will happen. It will not turn to red or blue. A research chemist adds a measured amount of HCl gas to pure water at 25 degrees Celsius and obtains a solution with hydronium ions 3 into 10 to the negative 4 molar. Calculate the hydroxide. Is a solution neutral, acidic or basic? How are we going to perform this calculation? It talk about HCl gas. Hydronium ion concentration is given. Calculate hydroxide ion concentration. Is the solution neutral, acidic or basic? How are we going to perform this calculation? We are given hydronium ion concentration. What else do we know? We know the Kw, right? Remember, we know the Kw. Kw is the ionic product of water, which is 1 into 10 to the negative 14. So Kw basically is hydronium ion concentration times the hydroxide ion concentration. To calculate the hydroxide, so the Kw is 1 into 10 to the negative 14. So we know hydronium ion, which is 3 into 10 to the negative 4. So then the hydroxide ion concentration would be Kw 1 into 10 to the negative 14, and you divide it by the hydronium ion concentration, which is 3 into 10 to the negative 4. Right? Kw divided by the hydronium ion concentration. Like this. This value over this hydroxide. So 3.3 into 10 to the negative 11. Now we want to find out whether the solution is acidic, neutral or basic. Okay, how do you find out that? In a basic neutral solution, hydronium ion concentration and hydroxide ion concentration are going to be 1 into 10 to the negative 7. In a neutral solution, hydroxide concentration same as hydronium ion concentration, which is 1 into 10 to the negative 7. Okay, so this is the amount of hydroxide and this is the amount of acidic hydronium ions, right? So which one is more? 10 to the negative 4 or 10 to the negative 11 is more? 10 to the negative 4 is more. Hydronium ions are more compared to the hydroxide. So the solution is acidic. Okay. Okay. The pH scale. Now that we know how to find the concentrations, a better way that we can represent the amount of hydronium ion or the hydroxide ion is the concept of pH, the pH scale. pH basically is the log of your hydronium ion concentration. Okay, hydronium ion H3O plus. So pH is negative log H3O plus. The pH of a solution indicates its relative acidity. In an acidic solution, pH is going to be less than 7. And in a neutral solution, pH 7. In a basic solution, pH greater than 7. So the hydronium ion and pH has an inverse relationship. The higher the pH, the lower the hydronium ion and the less acidic the solution. Okay, so higher pH, you see over here, the higher the pH, lower the H3O plus and the less acidic. So higher pH means the solution is basic. Okay, I'm gonna quiet my phone so you will not get disturbed. Okay, so these are some of the pH values of familiar aqueous solutions. So here you see the neutral pH. The blue indicates basic and then the red indicates acidic. So from the neutral, then some of the acidic components are milk about 6.4, urine 4.8 to 7.5, rainwater, beer, vinegar. Vinegar is also acidic. Remember, vinegar is acetic acid, which is a carboxylic acid, and a weak acid 2.4 to 3.4, lemon juice, and then stomach acid 1 molar hydrochloric acid. So they are all acidic. And some of the basic aqueous solutions, seawater 7 to 8.3, and detergent solutions are basic. Milk of magnesia, you may have heard that it is an antacid, that if the acidity is much in the stomach, you take milk of magnesia. It is a basic ingredient, so that will neutralize the acidity of the tummy. Household ammonia, again close to 12, 11.9. Sodium hydroxide 13, lye 1 molar sodium hydroxide 14. Okay, the relationship between Ka and pKa. Remember, we talk about how to calculate the pH. pH is negative log of pH is negative log of hydronium ions, right? Okay, I was looking for you. Remember, the pH equals negative log of H3O plus. Now, similarly, remember we talk about Ka. Ka is the acid dissociation constant. So we can do pKa is also going to be negative log of Ka. Okay, pKa negative log of Ka. A lower pKa correspond to higher Ka. Always hydronium ions and pH has an inverse relationship. Similarly, Ka and pKa also has an inverse relationship. A lower pKa meaning higher Ka. Lower pH means higher hydronium ion concentration because it's log term. Okay. pH, pOH and pKw. So we learned previously Kw is the ionic product of water, hydronium times hydroxide, which is 1 into 10 to the negative 14. So if you want to find out the pH, we can find the pH from the hydronium ions, negative log of hydronium ions. Similarly, pOH would be negative log of hydroxide. And pKw is this pH plus pOH together will give you pKw. In a neutral solution, if the pH is 7, pOH also 7, 7 plus 7 is 14. So 7 would be for a neutral solution, but it could be acidic or it could be a basic. But when you add the two together, the pKw would be 14 because the Kw is 1 into 10 to the negative 14. So how do you find pKw? So the pKw is negative log of Kw, negative log of 1 into 10 to the negative 14. So you can put this into your calculator and see what you get. Okay, negative, okay, do it with me right now. I'm also doing it. I know it is 14, but giving you some time to do that. Go ahead and put your number into your calculator and find out what is the negative log of 14. -14. Okay, so you have to put log and then 1 into 10 to the negative 14. That will give you negative 14. With that negative 14 and this the negative at the front will give you a positive 14. Okay. So pH plus pOH equals pKw for any aqueous solution at any temperature. Since Kw is a constant, the values of pH, pOH, hydronium ion and hydroxide they all are interrelated. If hydronium ion concentration increases, hydroxide decreases and vice versa. If pH increases, pOH decreases and vice versa. Okay? pH and pOH both cannot be increased at the same time because the pH plus pOH is a constant which is 14. If one increases, the other one decreases. You can see in this table relations between hydronium ions, pH, hydroxide and pOH. So these are more acidic. So the neutral hydronium ion 1 into 10 to the negative 7. In terms of pH, that's 7. And hydroxide the same in a neutral solution 1 into 10 to the negative 7. pOH also 7. Now if it is basic, you can see pH increases 8, 9, 10, 11, 12 like that. pH increases. And then what about the hydronium ion? Decreases because they have inverse relationship. Okay. And in a basic solution, hydroxide ion increases. You see it's increases. What about the pOH? pOH decreases. Similarly, in acidic solution, you can see hydronium ion going to increase, right? It's going to increase. What about the pH? pH decreases. Hydroxide ions decreases and then the pOH increases. pH decreases, pOH increases. Okay. Okay, calculate hydronium ions, pH, OH minus, pOH for each solution at 25 degrees Celsius. How are we going to do that? So you have a 0.3 molar nitric acid. You want to calculate hydronium ion concentration, pH, OH minus and pOH. So for 0.3 molar nitric acid, molar nitric acid, 0.3 HNO3. So nitric acid will dissociate to give you nitrate ion and a hydronium ion. So in water, it will give you H3O plus NO3. So you want to find out the hydronium ion. So the molar ratio 0.3 molar nitric acid will give you 0.3 mole hydronium ion. So to calculate the hydronium ion, since we just found out from the molar ratio hydronium ions H3O plus are going to be 0.3 molar. How do you find pH? pH is going to be negative log of H3O plus, which is negative log of 0.3. Do this number to your calculator and find out what is negative log of 0.3. Negative log of 0.3, and that would be 0.52. So put the numbers into your calculator and also see if you get 0.52. Okay, and then we want to find out the hydroxide ion concentration. How do we find the hydroxide? So we found hydronium ions, we found pH, and then the hydroxide, remember Kw equals H3O plus times hydroxide. So then the hydroxide would be Kw over hydronium ions. So Kw is known, 1 into 10 to the negative 14, hydronium ions 0.3. That will give you hydroxide ion concentration. And then from that we can find out pOH. pOH going to be negative log of hydroxide. Hydroxide is this amount, negative log of 3.3 into 10 to the negative 14, which is 13.48. Okay, so do this put this into your calculator and do your own calculations to make sure that you get these values. So the next one, you are given 0.0042 molar calcium hydroxide. You want to find out the same things, calcium hydroxide. So calcium hydroxide, again, it's a strong electrolyte. It can dissociate to give you calcium ions and hydroxide. There are 2 hydroxide here, so should be 2 hydroxide. So you start with 1 mole, 1, 2 hydroxide. So then if you have 0.002 calcium hydroxide, 0.042 calcium hydroxide, so it has to be 2 times this amount would be hydroxide. So hydroxide is 2 times 0.0042, which is 0.0084. So pOH going to be negative log of hydroxide, 2.08, and then we can find out the hydronium ions going to be Kw over hydroxide. Kw 1 into 10 to the negative 14, hydroxide be found. So the hydronium concentration is this amount. pH, negative log of hydronium ions, negative log 1.2 into 10 to the negative 12, 11.92. So that is how you can calculate pH, pOH, hydronium ions, hydroxide ions for a strong electrolytes, because they completely dissociate into ions. So we can go by their molar ratios, okay, if the concentrations are given. Okay. So we talk about the pH. Now how do we measure the pH of an aqueous solution? So there are several ways. So the most common ways to find out the pH is by using a pH paper. So pH paper indicates a rough estimation of the pH of the solution by comparing it to a colored chart. You will see these in our lab very often when we are performing experiments. You pick a pH paper and then put it into the solution and check to see what is the pH of the solution. So the pH paper will become dark red if it is very acidic, red. And then kind of the red color fades, and then it comes to the neutral for this color, and then as the pH increases, it becomes green and very dark blue. So that gives us a rough estimation what is the pH of the solution. But if you want to find out exactly what is the level of the pH with the proper numbers, you have to use a pH meter. Now this is a sodium hydroxide solution, very basic. You can see it is giving us 10.13. If you put a pH paper into sodium hydroxide, it will give you see here sodium hydroxide, a blue color. So that blue, it could be this blue or this blue. And yes, we know it is basic, around 10, 11. But the pH meter tells you exactly with the proper number what is the pH of the solution, 10.13. Okay. So we can talk about Bronsted-Lowry acid-base definition in the next session. Bye-bye.